Today, we're delving into Unit 3.4 of the first half of General Chemistry, which covers Avogadro's number. If you find value in this video, please like it and let people know about the channel because it really does help spread the knowledge. Avogadro's number is a fundamental constant, a number that does not change in chemistry, that represents the number of particles, atoms, molecules, or ions in 1 mole of a substance. It came about due to even extremely small measurements of molecules containing large numbers of molecules. For example, 5 milliliters, or 1 teaspoon of water, contains approximately 2 times 10 to the 23rd water molecules. Avogadro's number is defined as 6.22 times 10 to the 23rd, which means that there are 6.022 times 10 to the 23rd particles in 1 mole of any substance. The unit mole is one of the most difficult concepts for students to grasp and is vital to chemistry from here on out, so I'm going to try and really hit it home. Just like the unit kilometer or mile is a measure of length, a mole is a measure of the amount of a substance. With all things being equal, there is the same number of bricks in 1 mole of bricks as there is in 1 mole of feathers. However, they do not weigh the same. Do 5 bricks weigh the same as 5 feathers? No. So when you are running reactions in chemistry, you need to calculate everything in moles. Think of it this way. Let's say you're building a fence. You have wood and screws. Do you weigh out equal weights of the wood and screws to see how many of each you need? No. You measure how long the fence needs to be, how long the wood is, and how many screws go into the wood, right? This is confusing because in chemistry we add mainly by weight. This causes issues because just like 5 pieces of wood does not equal the weight of 5 screws, the 5 grams of different chemicals does not always mean there are the same number of chemicals in that weight measurement. It is further complicated when 1 molecule of a given substance reacts with 2 molecules of another. We can visualize this in the balanced reaction of K2CO3 plus 2HCl going to 2KCl plus H2O plus CO2. It takes 2 of the HCl's to react with 1 of the K2CO3s. This is analogous to it taking 2 screws to fasten 1 2x4. Remember atomic mass units, AMUs, in the previous unit? Hydrogen, H weighs 1.00 AMUs, and oxygen, O weighs 15.999 AMUs. Combining the concept of AMUs and moles, we get molar mass. Molar mass is the mass weight of 1 mole of substance expressed in grams. So 1 mole of hydrogen weighs 1.008 grams, and 1 mole of oxygen weighs 15.9999 grams. This leads us into interconverting mass, moles, and number of particles, which is fundamental to many areas in chemistry. For example, let's say you have an acidic solution that you want to neutralize. You know that you have 0.43 moles of hydrochloric acid, HCl, in that solution, and you want to know how much sodium hydroxide to add. The equation is HCl plus NaOH going to NaCl plus H2O of F. First, you notice that it's a 1-to-1 chemical reaction, meaning that 1 molecule of NaOH is needed to react with 1 molecule of HCl. Since NaOH comes as a white solid pellet, you want to know how much you need to add. To calculate this, you need to know the molecular weight, the mass in grams of 1 mole of NaOH. Looking at the periodic table, you see that sodium Na weighs 22.990 grams per mole, oxygen weighs 15.999 grams per mole, hydrogen weighs 1.008 grams per mole, so the total weight is 39.997 grams per mole. However, you only need 0.43 moles, not 1 mole. So you multiply the 39.997 grams per mole by 0.43 moles to get 17.20 grams. Using dimensional analysis is highly recommended doing any type of calculation in chemistry to make sure you're keeping track of the units. For this, it would look like 1 mole NaOH divided by 1 mole HCl times 39.997 grams NaOH divided by 1 mole NaOH times 0.43 moles HCl equals 17.20 grams NaOH. Using the dimensional analysis technique allows you to cross out the units and make sure you're following the math correctly. An example of determining moles from mass is as follows. You have 22 grams of gold, Au, and you want to convert that to moles. Looking at the periodic table, the molecular weight of gold is 196.967 grams per mole. Using dimensional analysis, once again, the equation is 22.0 grams Au times 1 mole Au divided by 196.967 grams Au equals 0.112 moles Au. Remember, the molar mass is just a ratio, meaning that you can flip the numerator and denominator as needed. 1 mole Au divided by 196.967 grams Au reads in 1 mole of gold there is 196.967 grams of gold, and 196.967 grams Au divided by 1 mole Au reads 196.967 grams of gold equals 1 mole of gold. Both of which are true. Converting moles or grams to particles is seldomly used in chemistry, but for completeness, I will show you how to set it up with dimensional analysis. Say you want to know how many molecules are in 48.2 grams of NaOH. The equation would look like 48.2 grams NaOH times 1 mole NaOH divided by 39.997 grams NaOH times 6.022 times 10 to the 23rd molecules of NaOH divided by 1 mole NaOH equals 7.26 times 10 to the 23rd molecules of NaOH. Based on what you learned, think about the following question. Calculate using dimensional analysis how many grams of oxygen you'd need to react fully with 0.81 moles of methane using the following reaction: CH4 plus 2O2 going to CO2 plus 2H2O.
Thank you so much for spending your valuable time learning and bettering yourself. If you like the video and want to learn more, donate, or get tutoring, please check out my website, nocollegeneeded.org. You can use the code NCN for 20% off tutoring and any supplemental material.